let's look at an example of approximating an instantaneous rate of change by actually doing some calculations, by finding nearby average rates of change. So let's approximate the instantaneous rate of change of this function, 1 over 4x squared minus x, at x equals 1. So remember, so here's x equals 1, so we're going to start with this point right here. So this is 1 f of 1, and turns out f of 1 is minus 3/4. Okay? So to find an instantaneous rate of change, remember what we're going to do is instead find an average rate of change. We'll move over here to a different x-coordinate b, and we'll find the average rate of change on the interval from the x value we want, which is 1, over to our second x value. And then we're going to move b towards a, or towards 1. But we're going to have to do this calculation for several different values of b as b sort of moves towards 1, just so we can see where all of these secant slopes are headed. So let's make a table. So we're going to use several different b values, and we're going to calculate the average rate of change. Okay, so let's start with b equals, well, let's make b way too big. Let's start with, how about b equals 4? Okay, so then our average rate of change is going to be f of 4 minus f of 1 over 4 minus 1. F of 4, so 16 over 4 is 4, minus 4 is 0, so 0 minus negative 3 over 4 over 4 minus 1 is 3, so this is going to be, let's see, positive 1/4 it looks like. Okay, so that means the secant slope from x equals 1 over to x equals 4 is positive 1/4, which looks about right, at least on the graph. Okay, but clearly 4 is way too far away from 1. The idea with the instantaneous rate of change is to approximate the instantaneous rate of change, we need to find the average rate of change over a small interval, but this interval from 1 to 4 is way too big. So let's make it smaller. How about we go to 2? So now we're going to find the average from 1 up to 2. So right here. You can see that the secant slope here is going to be small but negative this time. But let's actually do the calculation. So this is going to be f of 2 minus f of 1 over 2 minus 1. And off screen I have a little calculator set up so I can just tell it what x values we're using, and it's going to do the calculation for me. This time it looks like we get minus 1 over 4. Actually, it's using decimals, so I won't pretend that this is exact. I suspected that it is exactly minus 1/4, but minus 0.25. Okay, and that looks about right. But again, to approximate an instantaneous rate of change, we need the interval in x values to be small, and going from 1 to 2, that's actually still pretty big. So let's make our b value, how about 1.1? Let's cut to the chase and make b and 1 very close. So now we're moving b all the way over to here. So this is going to be f of 1.1 minus f of 1 over 1.1 minus 1. And you see what's happening here with this secant slope expression is that the denominator is getting very small because we're making b very close to 1. But the numerator is also getting very small because since the two inputs to the function here are very close, the outputs will also be close. So the numerator and denominator of this fraction are getting very small, and somehow those balance out. Right? That's the sort of key idea with this secant slope idea. As we make the interval smaller and smaller, the numerator and denominator both get small, but they somehow get small together, so that the resulting slope doesn't get huge and it doesn't get tiny. It could in some examples, but okay, so when I do this calculation, I get minus 0.475. Okay, so that's a pretty good approximation. You know, if we didn't need too much accuracy for our tangent slope, this would be a decent approximation, minus 0.47 or 0.48, depending on how you round. But, you know, in the grand scheme of mathematics, 1 and 1.1 are still very far apart, right? When it comes to real numbers, a tenth is actually pretty big in some contexts. So maybe instead of 1.1, we should try 1.01. So that's going to give us f of 1.01 minus f of 1 over 1.01 minus 1. And when we calculate this one, I get minus 0.497 and change. So I'll round it here to 4.975. Okay, that's pretty good. But what about 1.001? You know, since we want to make this interval from 1 to b, our b value here, since we want to make that interval very small, well, real numbers can get very close together. So no matter what b value we've chosen, we can always make the interval smaller by choosing an even closer b value. So this time with 1.001, I get negative 0.49975 and change. Okay, but we could go even closer. How about 1.0001? So from 1 to 1.0001. Okay, I got negative 0.499975 and change. There's some other digits out here. So, right, the idea that we had, we're going to stop here, even though, you know, we could go further. We could add more zeros. But remember, the reason that we were doing this is we were hoping that as we make b closer and closer to 1, we were going to see what happens to these secant slopes. Our hope was that these secant slopes ought to somehow head towards the tangent slope. So if we look at these values, these slope values, negative 1/4, negative 4.75, negative 0.4975, negative 0.49975, and so on, what value are these heading towards? Are these grouping around some number? Well, yeah, it looks like the smaller, or the closer b gets to 1, the closer these slopes are getting to minus 1/2. So that means that we think, or it would be a good guess, that the tangent slope should be minus 1/2. Now this really is a guess. We haven't proved anything. But if you look at the graph, if we start with this point and we graph a line through this point that has slope minus 1/2, that's going to, let's see, over 2 and down 1, so about to here. If we draw this line, it does look like it's tangent. So that makes me believe that this process that we used to guess this tangent slope, that this is an effective process. So it does work, but there are two problems with this. First of all, it's not very mechanical, right? We had to use a lot of guesswork to make this work out, so there's really no way we could, say, program a machine to do this for us, so it's not a mechanical process. The second problem with this is, for this particular example, it was kind of clear that these numbers were heading towards minus 1/2, right? We're just getting closer and closer to minus 1/2, but for other examples with messier numbers, these slopes, even if they're settling down, it might not be clear what number they're headed towards. They might be just headed towards some messy decimal, and we don't really know what to call that decimal, right? So for this example, we just made a nice round even guess of -0.5, but it might not be clear in general what to guess as you generate more and more approximate secant slopes. So this process of generating better and better approximations by making B closer and closer to A, it's a good idea, but in practice it has some severe limitations. So we're going to have to eventually come up with a better way of doing this.